Hello guys, today we're going to go through the chapter 3.4, multiple expansion. Okay, but we're not going to finish the entire section for 3.4. Uh, we will first introduce half of the section, which is 3.4, multiple expansion. So first of all, let's consider some situations where you have more than one charges. Now, if you're very far away from a localized charge distribution, which is not only one point charge, instead it's charge distribution, then it looks like a point charge if you're far away from that. For example, if we draw the picture, you may have some charges. It might be positive, might be negative, it might be two charges or even more. But if you're, let's say you're standing very far away, which is this point P, when you look at the collection of the charge distributions, if you're far enough, then um, it looks like a point charge. Let's say you have a lot of charges distributed here and there, and they're far away, then a good approximation is a point charge, and then the potential could be calculated using the Coulomb's equation. And here, r is the distance between your let's say your location that you concerned to the collection of the charges. And the Q will be the total charge, of course. We have often used this as a check-on formulas for V. But what if Q is zero? For example, if the total charge of this charge collection is zero, then your potential becomes zero. You might reply the potential is then about zero. And of course, you're right in a sense. And indeed, the potential at large R is pretty small, even Q is not zero. So if it's far away enough, uh, even the net charge is non-zero, you still should get about zero potential at the location you concern. But here we're looking for something a bit more informative than this um, than this term. This is only one term, and later on after this section, you will see this is only the dominant term um, for the potential of a collection of charge distribution. So this is a dominant term, but you will have more terms, or we will have some more informative equations than this single term equation. Now let's see easiest case. If you have an electric dipole, which consists of two equal and opposite charges, which is plus Q and minus Q, which is shown here in figure 326. You have plus Q and negative Q, and then it's separated by D. And let's find approximate potential at point far from the dipole. Let's see, the point is here. We want to find the potential here. And the distance between the location here and the center of plus Q and minus Q is R. Notice that this is the center of plus and negative Q. Now let's see the solution. Of course, the solution will be, let's calculate the potential from plus Q to this point, and then calculate the potential for negative Q to this point. Then if we do a sum, we will get the total potential from this dipole. So that's easy. So V equals to 1 over 4 pi epsilon Q over R plus subtracted by Q over R negative. So this is the term for the potential generated by positive charge, and this is for negative charge. You simply sum them up, you will get the potential from this diaper. And now let's see, from the law of cosines, we know R plus square equals to R squared plus D over 2 squared subtracted by RD cosine theta. Now let's see, R plus means um, from the positive charge to your let's say your location P, and then this R plus equals to R square plus this is D over 2 squared subtracted by this theta. This is from the law of cosines. If you consider the upper triangle in this figure, which is from Q plus Q to the center and then to P. This is the upper triangle. And for lower triangle, you will have R minus squared equals to R squared plus D over 2 squared plus RD cosine theta. And then based on this equation, what you can have is, first, let's see if R is much longer than D, then the third term is negligible, which means this term is negligible. Now you will have only two terms, which is 1 over, okay, you have two terms, which is R plus minus squared equals to the first two terms. And from the first two terms, you can yield an equation which is shown here. 1 over R plus minus is approximately equals to 1 over R, 1 plus minus D over 2R cosine theta. We're not going to derive this equation in details, but let's believe the textbook is right. Then 1 over R plus subtracted by 1 over R minus approximately equals to D over R2 R squared times cosine theta. Based on this approximation, you will get this equation here. And then if you have this equation, then your V will be 1 over 4 pi times epsilon times QD cosine theta over R squared based on this equation. Because here, this term is the term that you needed to calculate the potential. Now you just substitute these terms by a single term, which is here, and then you get the final equation shown here. So the potential of a dipole goes like 1 over R squared at large R. Remember that for a point charge, it goes like 1 over R. However, here we see the potential of a dipole goes like 1 over R squared. That means it vanishes more or faster than a point charge. As we might have anticipated, it falls off more rapidly than the potential of a point charge. If we put together a pair of equal and opposite dipoles to make a quadrupole, then the potential goes even faster, which is like 1 over R cubics. And for back-to-back quadrupoles, which is octupole, it goes like 1 over r to 4, and so on. So here, the picture shows a monopole, dipole, quadrupole, and octopole. And the V, we can see the V falls off. In monopole case, it falls off 1 over that it vanishes faster, 1 over squared. And for it's 1 over weak for hit 1 over R4. So it's uh, some idea of quark, and, and we see um, the more charges you have, uh, so vanishes faster when you move the constellation from the section of the chart. And let's see some other example. Okay, let's see. Okay, microphone. There was microphone settings. Now I think it's getting back. Now you can hear my voice again. This example, very special part of we pose now to systematic expansion of any localized part of 1 over r. And uh, let's figure to define the element of variable here. Now you have distribution, which is um, a it's a density chart in a and a, now distribution of charge and have you uh, there's something wrong with my let me pause. Sorry, there was something wrong with the computer. Um, I paused the recording now. Let's resume the recording. So here is a distribution of, let's say, volume charge distribution. And the distance between, let's say, a d tau to P is defined as R. And let's say the origin from P is R, and the origin from d tau is R prime, and the angle is alpha shown here. If we set up the situation in this case, then V equals to 1 over 4 pi epsilon 0, and then times the integral of 1 over R rho d tau. That's the volume integral for the entire charge density distribution. And using, again, the law of cosines, of course, the R squared equals to this R squared plus R prime squared subtracted by 2 R prime R cosine alpha. And the alpha is the angle between R and R prime, then R equals to this R square root of 1 plus epsilon. And then here epsilon equals to this equation. And after a lot of um, derives, you will finally get the conclusion of 1 over r equals to this term. And substitute this term into the previous equation, you will have the conclusion for the uh, potential of a collection of charge density, which is 1 over 4 pi epsilon 0, and then the sigma from n equal to 0 to infinity, 1 over r n plus 1. So note that n is from 0 to infinite number, and the integral of r prime to power n and pn cosine alpha rho r prime d top prime. Or if you write it into more clear or explicitly terms, you have infinity terms. When n equals to 0, then it's 1 over r, which is shown here, times rho d top prime. And when n equals to 1, you get this term. When n equals to 2, you get this term. Because n is from 0 to infinity, then you have infinite terms. And here we didn't go through the entire or the detailed derives because if you're interested, you can derive it by yourself or with the help of those equations. But otherwise, I prefer you to remember or utilize the conclusion here. The interesting thing in the conclusion is when n is from 0 to infinite number, um, it indicates different multiples. For example, when n is 0, that term indicates the potential term here. If you look at this term, actually, what's that? 1 over 4 pi epsilon 0 times 1 over r, then a charge integral. This term is just the potential for a point charge. And if you look at the second term, this is a term for the potential of a dipole distribution. And then this is quadrupole. So the interesting things becomes um, the desired result is multiple expansion of V in powers of 1 over R. So the first term is monopole, the second term is dipole, etc. And here, this equation is the most useful equation. It describes the potential generated by, let's say, a collection of um, charges. It could be point charge. It could also be not point charges, but a continuous charge distribution, like a volume charge distribution. Okay, so ordinarily the multiple expansion is dominated by the monopole term. If you look at this equation, you see for the second term or the dipole term, it's a 1 over r squared. So it vanishes fast. And for the higher order, let's say multiple charges, let's say quadrupole, it vanishes by 1 over r cubic. It vanishes even faster. So the dominant term when r is, let's say, when this r is a big number, the dominant term is the first term, which is the okay, is a monopole term. And then it could be written in this equation, and Q, of course, is the volume integral of the total charge. This is what we expected for the approximate potential at large distance from the charge. For a point charge at the origin, the potential of monopole is exact the potential, not only a first approximation of the potential at a large r. In this case, all the higher multipoles vanishes. If the total charge is zero, then the first term becomes zero because this integral becomes zero. So the first term is zero, then the dominant term becomes the second term, which is a dipole term. Then the dominant term in the potential will be the dipole term. And since alpha is the angle between r prime and r, if you look at the figure here, this is alpha. Then the dipole potential can be written more succinctly, which is dipole equals to 1 over 4 pi epsilon 0 r squared, 1 over r squared times the normal vector of r, then dot product the r prime rho theta. So here you see cosine alpha is gone because this is a vector product, a dot product of two vectors. It contains the cosine alpha. So here you don't have to write the cosine alpha again. Then this integral is called the dipole moment of the distribution. Then if we let the dipole or P or dipole moment equals to r prime rho theta, then this previous equation shown here could be written into this term. The potential of a dipole equals to 1 over 4 pi epsilon 0 P dot product the normal vector of r over r squared. So here, what you did for this equation is you just substitute this term by P, which is a dipole moment. So the dipole moment is determined by the geometry, which means the size, shape, density for the charge distribution. And the equation 398 translate in the usual way for point, line, surface charge. Then if it's not a continuous distribution of charges, instead, if it's a charge collection of some point charges, then the dipole of the point charges becomes this equation, of course, from integral into a sum. For physical dipole, which is equal and opposite charges plus q and minus q, then the dipole moment equals to, let's take it into the equation here. It equals to q r prime subtracted by q r prime minus, or q r prime plus subtracted by r prime minus, which is qd, because let's say if you have plus q and minus q, and let's say this is r plus, this is r minus from the origin. Of course, they are all, let's say they're all vectors, then r plus subtracted by r minus becomes this vector, and we define this as d. So, and this is a vector. So the dipole moment becomes q times vector d, and the vector is from the negative charge to positive charge. So the direction is from here to negative to from negative to point to positive charge. And the figure is shown here. Okay, so that's the concept of the potential for multiple charges. And that's all for this lecture. We'll continue to describe the multiple expansions in next class. See you guys. Thank you.